Hey, AP Chemistry. We're starting Unit 3, and I'm going to break these into several smaller videos for you. This first one is just an introduction to thermochemistry. So what is thermochemistry? Well, you should know that therm refers to heat. So what we're looking at here is the relationship between chemical reactions and energy changes that involve heat. You need to know that energy does not have mass, but it does have the capacity to do work or to transfer heat. Work is energy used to cause an object to move, while heat is the energy used to increase the temperature of an object. Throughout the year, we will be often talking about kinetic energy and potential energy. So let's take a quick look at the difference between the two. And you will need to be able to calculate kinetic energy for your test. Kinetic energy is the energy of motion. This depends upon two things, mass and velocity. Please note, you must be in kilograms and meters per second. A lot of times, problems will give you the mass in grams. You need to convert that to kilograms first. Kinetic energy is simply 1/2 times the mass times the velocity squared. Don't forget to square the velocity. Well, why do we need to care about kinetic energy? Atoms and molecules most of the time are in motion. If they're in motion, they have kinetic energy. So we need to consider that. Also remember that kinetic energy is related to heat or to temperature. As the temperature increases, molecules have more energy, therefore their kinetic energy increases. Potential energy, on the other hand, is stored energy, and this depends upon position or height. For example, at the top of a roller coaster, you have the most potential energy, while at the bottom of a hill, you would have all kinetic energy. Potential energy is simply the mass times gravity times height. Mass is kilograms, gravity is meters per second squared. Usually it's 9.8 meters per second squared, and the height is in meters. One other little thing here while we're at it is Coulomb's law, which we've already talked about, but it's also known as electrostatic potential energy. And you can calculate that force by multiplying a constant by the two charges and divided by the distance squared. I'm just throwing that out there because it kind of fits in here with what we're talking about. Let's take just a brief look at some of the energy terms you need to be aware of. Joule, or capital J, is the international unit. But joules are really small, so usually we refer to things in kilojoules. And just remember that 1 kilojoule is 1,000 joules. Now there's 2 calories, one with a lowercase c, one with a capital C. Lowercase c is simply the amount of energy needed to raise 1 gram of water 1 degree Celsius. Important that that goes with the word water. 1 big calorie is equal to 1,000 little calories. And 1 little calorie is 4.184 joules. This also is going to go into specific heat when we get there in a little bit. Work is the energy transferred when a force moves an object. Work is very simply found by multiplying the force and the distance. This is something we do a lot in physics. And heat is simply the energy transferred from a hotter object to a colder one. Now, I threw the nutrition facts label on here just to kind of relate something to your daily life. If you look on this particular label, I honestly have no idea what it's for, you'll see that it says calories 20. Now that's capital calories. So lowercase calories would be 20,000. I just want you to know that those nutrition labels do talk about capital calories, and that's what you're taking in when you eat or drink this substance. Students struggle in thermochemistry because you have to start thinking about the system versus the surroundings. Is the system doing work on the surroundings? Are the surroundings doing work on the system? System simply refers to the chemical reaction. Now, I kind of disagree with this picture I found on the internet. It says the system are all the water molecules. Honestly, I would think of it as just the ice in this case. The surroundings are everything else, the container, the water, the air. So let's say we threw some chemicals into water. We cannot measure what's happening to the chemicals. We can, however, measure what's happening to the surroundings. So if you put a chemical into water and the water gets hotter, well, where did that heat come from? It came from the system. It came from the chemicals. So you need to start thinking about it in those kinds of terms. There's three kinds of systems. An open system is where matter and energy are exchanged with the surroundings. Closed systems can exchange energy but not matter, and isolated, nothing is going to be exchanged with the surroundings. So I always joke when somebody loses weight and somebody else gains weight that weight went from one person to the other. Of course, in science, this isn't possible because we're not a closed system. We're open systems, and that just doesn't happen. Let's tackle the first law of thermodynamics, and that basically just states that energy is conserved. That's it. There's internal energy, and that is the energy of the system. It's the sum of all the kinetic and potential components of that system. Since we do not usually know the numerical value of a system's internal energy, we simply look at what happens to the energy. What's the change in energy? The change in energy is simply the final energy minus the initial energy. By the way, anytime you're looking for change in anything, change in temperature, change in you name it, it's always final minus initial. And that's really important because sometimes it's going to be a positive value and sometimes it'll be a negative value. And those positive, negative things, they do have meaning. This is always found experimentally. Let's just look at change in E a little bit more. Change in E should have three things. It should have a value, a number, a unit, that's a label, and a sign that gives direction. When delta E is positive, that means that the final energy is greater than the initial energy. That means that the system has gained energy, so the surroundings have done work on the system. But when you get a negative delta E, it means the initial is greater than the final. The system's lost energy to the surroundings. Remember, if a system gains energy, the surroundings lose energy and vice versa. And this will be important in the lab that we do during this unit. We're going to monitor the change in what happens to the water. Well, whatever happens to the water, it's the opposite for the system. So if the water gets hotter, the chemicals, the system got colder. So keep that in mind. There are a lot of vocabulary words and different symbols that go with this unit. So let's look at how E is related to heat and work. Well, delta E is equal to Q plus W. Q is the heat that is either added or given off by the system. W is the work done on or by the system. So what am I talking about here? Sometimes the chemicals do work on the surroundings. Sometimes the surroundings do work on the system. And you need to be able to think about that in those terms and decide which direction things are going. When you add heat to a system, Q is positive, and work is being done on the system. Therefore, the internal energy increases. I always like to think about how would you feel if an elephant sat on you? Wouldn't heat be added to you? Wouldn't work be done on you? Wouldn't your internal energy increase? Okay, it's a silly analogy, but it kind of makes sense. When the system loses heat or it does work on the surroundings, they're both negative values and the internal system is going to lose energy. Let's just quickly define endothermic and exothermic, but we're going to talk about them later in the unit. Endothermic simply means when a system has absorbed heat and the temperature of the surroundings decrease. So if I'm the system and this room are the surroundings, if I suck all that heat up into me, I get hot. The surroundings cool off. Remember, we can't measure the reaction, but we can measure the air or the water. So if out here gets colder, where did that heat go? Into the system. And honestly, I remember this because of Spanish. In Spanish, en la casa, en means in. So it's going into the system. And that also helps to remind you that if something is endothermic, that means heat is a reactant because it's going into the reaction. Exothermic is the opposite. Heat is lost. Heat is given off to the surroundings. So if I release heat, the surroundings are going to warm up. And exo, I always think of like exoskeleton on the outside. Exo means being given off. So this would be a product. Hang with me for just one more slide. Let's just take a look at something called a state function. A state function is a property that is determined by the system's condition or state. This only depends upon the present state of the system, has nothing to do with the pathway that the system took to get there. So here's an example. If you drive from Chicago, Illinois to Denver, Colorado, your altitude is going to increase 4,684 feet. It does not matter how you drive from Chicago to Denver. You could drive from Chicago to New York to Florida to California to Denver, or you could just drive straight from Chicago to Denver. Either way, you're ultimately going to increase your altitude 4,684 feet because it's going to be final minus initial. This is a state function. The distance driven is not a state function because of the route you might take. So in this unit, you need to know that E is a state function. It doesn't matter how that change in energy occurs, just what was the final, what was the initial. Q and W, though, are not state functions.